when our group present name is Hydrogel 3D printer. I will present about the introduction. First, problem statement. The issues that we are focusing is most of syringe pump based printer have issues with retention, which is the ability of a 3D printer to stop and reverse instruction prior to movement between printed portion of each layer. Retention is important because it prevents material from leaking or during the non-extruding move, thereby unintentional extrusion or thin strings of material that can reduce printer fidelity. Next is objective. First, to help engineers who are in bioengineering field to produce a 3D printing machine for bioengineering application at an affordable price range. Next, to create complex geometry with high resolution in bioengineering application. To minimize any difficulty to a fabrication by utilization standard string size and lower fitting. Next, increase bioprinter in volume. And lastly, increase performance of hydrogel extruder by enabling use of small size and increase the speed. Scope. This hydrogel 3D printer will be targeted to researchers, students, and university for their experiment, research, and studies. Furthermore, this printer will be targeted for newly started companies so that they don't have to come up with a huge capital since it is going to be cheap and affordable.
For the product description, our hydrogen 3D printer is constructed by two main parts. The first part is the body part. The body part is the main part that functions to move the nozzle along three axes X, Y, and Z. The movement is powered by the NEMA 17 stepper motor, 8mm threaded rod, and C8UU as the linear bearing and timing belt. The second part is the syringe pump extruder. This functions to extrude the hydrogel that been filled inside the 60cc syringe and pushed by the force of the NEMA 23 stepper motor. Our hydrogen 3D printer design is basically on the DIY 3D printer. The only difference is the material that been extruded and the extrusion mechanism. Based on this simulation, this is basically how our 3D printer works. At the every end of the axis, we plug in a micro switch as the end stop. Software such as Malin firmware and Pronto Face software is used to convert the CAD file into STL file and produce the printed product. Due to the hydrogel is easily ruptured, the hydrogel is extruded into a support bath which consists semi-solid gel. This is to support and hold the hydrogel into desired shape.
For engineering analysis, we run a dog bone test or tensile test on a standard dog bone shape made up of ABS. For this, we do not use PLA because of the insufficient information on the mechanical properties of the PLA, which caused the test could not run the simulation for the tensile test. ABS also show that it is also possess the nearly same mechanical properties to the PLA. For this test, we already fixed the dog bone to the end point of the bone, while we applied 200 Newton force on the other end point of the bone. From the table, we find a high quality mesh also means that there is an optimal balance between the computational cost and the level of fineness achieved. A low quality mesh will not only result in inaccurate simulation results, but might even cause to the solver to produce an error due to instability. For the hydrogel engineering analysis, Hydrogel is a newly synthesized material which we cannot finalize its mechanical properties. Some of the past research already came up with the mechanical properties but still incomplete to run the tensile test. For further engineering analysis, we may do this analysis after we succeeded to fabricate our 3D printer and finally printed the hydrogel into dog bone shape and test for the tensile test manually.
I will continue with product costing for our project, Hydrogel 3D printer. These are costs for all material that we use to make Hydrogel 3D printer prototype. On the left table are the material that we use to make shrink pump extruder, and on the right table are material that we use to make 3D body parts. I assume that the material costs for prototype are equal to the cost for mass production because I need to get sales price per unit that I will present later. And this is a variable cost. This table are the summary of variable cost for our product, and on the right is calculation that I made to get total product that can be produced in a month, and also to get me variable cost per unit. Okay, this is a total fixed cost to produce hydrogel 3D printer for a month. I will continue with a sales price per unit. As you can see, the cost for single unit is 590 ringgit, but I'm taking 30% of profit margin. So total our selling price for hydrogel 3D printer is 674 ringgit. And lastly, this is a break-even point. This calculation is contribute margin, which is used in BEP formula, and we get 96 unit for BEP. It means that this is a minimum unit that company need to sell per a month to ensure the company can be sustained.
As we can see, this is the sustainability report that has been interpreted by SolidWorks software for our project. The weight of our project is at an approximation of 6 kg and it is built to last for 5 years. These are the data of assembly process, use, transportation and end of life of our project. Next slide refers to the environmental impact calculated by CML impact assessment methodology, which refers to the data of carbon footprint, total energy consumed, air acidification and water eutrophication. Okay, these are the top 10 components that contribute most to the 4 areas of environmental impact, which are carbon, water, air and energy. Okay, as we can see, after redesigning our project, only 2 components does not meet the requirement of sustainability, which are the threaded rod and the smooth rod. In our project, we have applied BMFU to the syringe pump component, where the number of parts of the component has been reduced after applying BMFA. Okay, next we can see that our newer design of the project is more sustainable compared to the older one. As for the conclusion, we have learned so many things during this project throughout the semester. With the enormous amount of help from our supervisor, we as a team believe that we have done good work and excellent cooperation is made. We have done a successful project by successfully creating a functional digital prototype. We have found that success in manufacturing requires continuous development and improvement on how the products are developed and produced. The implementation of DFMA is very effective and gives us positive results. All the objectives were achieved to produce good quality product, reduce part counts, reduce assembly time and minimize costs. Thank you.